Hello everyone, this is Karthikeya Jain, and for this project I've created a basic implementation of the paper, a simple framework for contrastive learning of visual representations. Now this paper was first presented by researchers at Google in the ISE conference in the year 2020. The paper introduces a new neural network architecture called SimCLR, which is short for the name of this paper. Now SimCLR is a self-supervised contrastive learning technique and was originally built for image data. In the original paper, SimCLR was trained on ImageNet and Cypher datasets and was shown to perform better than other supervised and self-supervised models at the time. Now, before proceeding further, let's make sure we understand the meaning of the terms semi-supervised learning and contrastive learning. So semi-supervised learning is a machine learning paradigm which deals with partially labeled datasets. And when applying deep learning in real world, one has to use a large amount of data to make it work well. However, the cost of labeling increases linearly as the dataset size increases. And also, labeling takes a lot of time, so time also increases. Model performance, on the other hand, only scales sublinearly. What that means is that you have diminishing returns, and because of that, labeling becomes less and less cost efficient. While on the other hand, if we are gathering unlabeled data, it is usually very cheap and it is usually readily available in large quantities. So semi-supervised learning offers a way to solve this problem by requiring only a partially labeled dataset and by being label efficient by utilizing the unlabeled examples for learning as well. The main idea behind contrastive learning is to learn representations that are invariant to image augmentations in a self-supervised manner. Now, contrastive learning pulls representations of augmented images of the same image closer to each other while simultaneously pushing different images away from each other in a representation space. SimCLR is one such contrastive approach, which essentially identifies the core components that are needed to optimize this objective and can achieve high performance by scaling this simple approach. Now, the approach of comparing embeddings is not new. We have seen that being done in Word2Vec and other language-based models like BERT, Roberta. SimCLR, at the time when SimCLR came around, there were other papers which were trying to do the same thing. They were trying to replicate the results, the success which they saw in NLP, and trying to replicate it for images. What SimCLR did differently were these four things. So, firstly, the composition of image transformations was different. Second, the nonlinear projection head. Third was the emphasis on temperature and normalization of the embeddings. And the fourth was using extremely large batch sizes and using a large number of negative samples. And we'll see each of these in more detail. So in composition of augmentations, let's say if you have a function and you apply that function to an image, what you get is a transformation of that image. Similarly, let's say you have a second function and you similarly apply that to the original image, you get another transformed image. You can get many augmented images like this, and each of them should have a similar representation in the representation space. Ultimately, the embeddings for all these images should be similar. What SimCLR does differently from other approaches which have done this before is that it combines the augmentations into a long chain. So it's like applying one function on top of the other, and you combine transformations, you apply them in a chain one after the other, and finally you get augmented image. And generally, this sequence is 5 to 6 transformations long, and these are stochastic in nature. So in SimCLR, what we do is for each image, we try to create embeddings. And using these embeddings, we try to find similar images. What this lets us do is learn from the embeddings. And by learning from the embeddings, you can learn certain features which are difficult to encode. So initially what you do is you start with a large encoding network. This was in the paper, they have used ResNet 50 as an example. You can use any encoder over here to encode your image. And what this does is it converts your image into a vector representation, which could be used as an embedding. After obtaining this embedding, this has been passed through a set of fully connected layers, which is known as the nonlinear projection head, because you have more than one layer. So basically you end up with a nonlinear combination of the values in H, and that is represented by Z. So the third important difference that SimCLR had with all the other models at the time was use of temperature and normalization. What SimCLR does is that after converting the images into the embeddings, it normalizes them and then uses this loss function on the top to basically calculate the similarity between images, and it tries to optimize that loss function. So first, what you do is you apply contrastive loss to all the normalized embeddings, and all the vector z's are on the surface of a unit circle. As you can see over here, it is being depicted by the circle at the bottom. And hence, what you're trying to do is you essentially try to bring together the embeddings which have a low contrastive loss, and you try to push away all the negative pairs of the images which are basically belonging to other images. So the temperature factor is pretty important, and SimCLR uses this temperature value of zero point 0.5. The temperature is used to stabilize the loss, and the lower the temperature is results in a better accuracy. Now, the fourth point which made SimCLR different from all the other approaches at the time was use of large batch sizes. In SimCLR, the images are divided into batches, and after generating the augmentations and their representational embeddings, we compare the embeddings across all the images in the batch. And we try to push away all the non-similar embeddings as discussed in the last slide. Now, since the objective can be interpreted as a classification over a batch of images, the batch size is actually a very important hyperparameter than usual. And the higher the batch size, the better it is. This whole training is done online, so you do not use a memory bank and you do not use any kind of storage for the negative samples. Now, we have talked a bit about the contrastive task. What that essentially means is that you start with an image, you create two augmentations of that image, and you pass it through a network. This network is called the encoder network. And what that does is it generates an embedding. Now, you use that embedding to compare the images. And before doing that, what we do is we pass it through a non-linear projection head, which converts this into a invariant representational embedding. And the embeddings created at this point are the ones which we use for comparison. So the augmented images which come from the same original image should have a high similarity compared to the embeddings which come from non-similar images. So in the data augmentation pipeline, what we do for each image is we take the image, we randomly crop it and resize the crop to the original image size, we flip it with a probability of 50%, then we add color jitter. So what I mean by color jitter is we play around with the values of brightness, hue, saturation, and after doing that, we apply a Gaussian blur to the image. Now, this transformation is applied to all images, and basically, this is applied twice to generate two different augmentations of each image. Now, the sequence of transformations in this order is not by coincidence. This is from the experimentation, and the researchers have tried a bunch of different sequences, and this is the best one they found out for the paper. In practice, changing the above pipeline ever so slightly can result in significant drop in performance. Now, earlier we discussed projection head, and this image basically tries to explain what's going on in the SimCLR network. We originally start with an image X, and we apply two transformations to it. And so T over here represents the transformation, and after applying these two transformations, you end up with two different augmented views of the same image, which are denoted by xi bar and xj bar. After that, we pass these images through an encoder to obtain the representation embeddings at h. And these values are again passed through a non-linear projection head, and we end up with values zi and zj. At the end, what we try to do is we try to maximize the similarity between the embeddings which come from the same original image. So here we'll try to maximize the similarity between zi and zj. Now, this nonlinear projection head is important because researchers have tried experimenting with different values. What they tried is they tried initially using the hi and hj values directly, but they found that they did not perform that well. They tried adding a linear projection head, but that again did not result in a significant performance boost. So adding this nonlinear projection head is pretty important. Now for the loss function, what we try to do is we use this negative log value because ultimately what you see inside the brackets is a fractional value. So the log value for that will be negative. So basically we're using the negative sign outside to negate that. And on top in the numerator, what you see is a similarity measure between the images which come from the same original image. So if we go back to the previous slide, as you can see over here, ZI and ZJ are two embeddings which come from the two augmentations that were created from the same original image. Looking at the math over here, SIM, similarity, that's a function which calculates the similarity. Now, this could be something as simple as cosine distance. The tau value which we see in the denominator of the numerator as well as the denominator is the temperature value. So this is something which is used to reduce the spikes in in the values of softmax distribution. And the lower this value, the better the accuracy. So in the numerator, what we have is basically a similarity between the embeddings which come from the same image. And at the bottom, what we do is we basically add up the similarity scores which we get for images that come from different sources. Basically, if we are looking at ZI, which is basically one of the embeddings which come from our original images, what we do is we compare it with all the other augmentations that were generated in this single batch of images, and we add up the scores for these similarity measures. Now, one of the last tricks that SimCLR paper introduces is called the global batch norm. And what that does is when you have a large distributed training system, for example, when you're using hundreds of TPU cores or GPU cores, this is what you use. In the original paper, they used 128 TPU cores, and in the most general cases, well, we use something called as batch norm. Now, batch norm is something which is calculated on each GPU. So basically, what you do is you calculate batch statistics on a single GPU, and then you subtract the mean and divide by the standard deviation from all the images in that batch. Now, global batch norm accumulates statistics across all the GPUs, and it synchronizes those values and then performs a single batch norm operation for all the images using this global statistic. The authors of this paper say that this is done to prevent a shortcut, and because the positive pairs are always on the same GPU, they can end up having a large contribution and can influence the results significantly. So if you have a small batch size, the contribution of these positive pairs is a lot, but the influence significantly diminishes when using global statistics. If the neural network finds a shortcut, the task will be easier to solve, and the embeddings learned would not be that good. So now coming to the implementation, well, I've done some simplifications to the original implementation of SimCLR in the paper. I'm using a simpler encoder instead of ResNet 50. So what I'm using is just a bunch of convolutional 2D neural network layers instead of the complete ResNet 50. What this does is that when you're using a larger network, it takes more resources to train. It takes much more time to train. And using a simpler encoder, basically what I end up having is a model which runs a bit faster. It takes less resources, although it's not as accurate as the results which were shown in the original paper. Also, I've used a lower temperature value of zero point 0.1. Now, what this does is that, so basically a lower temperature value is better. It ends, basically you can end up with a better accuracy if you use a lower temperature value. And also I have used a simpler baseline model. So in the original paper, they were comparing it to models like ResNet 50 and other uh, much more complex supervised learning networks. Now for this project, I am using the STL10 dataset. This dataset was partly inspired by Cypher10. So this dataset again has just 10 classes. The images are 96 by 96 pixels and are all color images. So the data is a bit more complex compared to the original Cypher data, which was only 32 by 32 pixels. We have 500 training images and 800 test images per class. So that means we have a total of 5,000 training images and 8,000 test images. And we have 100,000 unlabeled images, which we need to learn from. And this is a very common data set which is used for unsupervised and self-supervised learning. All these images, they basically are acquired from the ImageNet dataset. Now coming to the results of my implementation, well, as you can see in these graphs, I have three different models. So one is the supervised baseline model, the other is supervised fine-tuned model, and the third one is self-supervised pre-trained model. So what this means is that basically in contrastive learning, you first pre-train a model, you learn the embeddings, And using this model, you fine tune it later and you get the supervised fine tuned model. The supervised baseline model is trained only on the labeled data set. In our original data set, as we saw that there are only 5,000 training images which are labeled. The blue line represents the supervised baseline model. As you can see, it performs a bit better than self-supervised pre-training model. Now, the self-supervised pre-trained model was something which was learned completely on its own from the embeddings. And as you can see, the accuracy is a bit lower compared to supervised baseline model. But after pre-training, if we take this model and we fine tune it further using the label dataset, the accuracy sees a significant bump. And as you can see, it outperforms the supervised baseline model. Similarly, for the loss, as we can see that loss significantly decreases after we fine tune the model. So over here, I've included a few references. The first reference over here is the dataset link, which I've used for this problem. The second link is the link to the original paper. And the third link is basically a GitHub link for the original code implementation of SimCLR. So in this project, I got a chance to learn about contrastive learning and self-supervised learning. I also got a chance of learning how to use unlabeled data in a semi-supervised manner. So basically learning how to create embeddings and use them for learning. And this approach, I believe, can also be used for annotating large amounts of unlabeled image data. Um, Another thing which I learned as part of this project was creating custom layers in Keras. So as I mentioned before, for creating augmentations, there are some layers which are pre-provided by TensorFlow and Keras, and they did not have something which could randomly add color jitter and grayscale images. So that was a custom layer which I had to create. And I also looked at how to use auto gradient in TensorFlow to calculate and to basically to calculate gradients and use that for path propagation.